Am I audible?
Yes, sir.
I hope my screen is also visible to all of you. Isn't
Yes,
it?
sir.
Okay. So let me just do a recap. So in the context of control, we are now trying to understand how do you design control. So we have seen that so for instance, let's consider you are trying to develop a control system for a jacketed CSTL. So there is a error to it, okay, and there is feed comes in, product goes out. There may be multiple feed coming in. Yes? F1, F2, F0. There is a flow rate, and you might recirculate. So this is the heating point. This is the coolant flow, and this may be your U. One of the U's, maybe, who knows, and F1, F2, and your product. So, there are ways. So we are initially looking for how to design a feedback system. Okay, considering the fact that you don't do overreact. So, for instance, there is some effect. Of course, there is some effect, and you correct it until it becomes proliferate. So, how do you do that? You use sensors to measure the actual scenario. For instance, let's say the product quality of F naught is the critical factor. So you would put a sensor corresponding to that. You draw a line, you make an analyzer transmitter that, and of course this analyzer, see, till this time it is hard line. Okay, this analyzer transmitter might go to an analyzer controller. So this will become electrical line. This is piping. This is signal. In fact, electrical signal. Okay. This analyzer controller you would feed in with the desired value, which is your set point. So based on the current value that it is received and the set point that you are given, it computes the error and also the corresponding action, control action, what you need to do. It eventually it produces a signal out of it that helps you to course correct. Okay, so then this will go to an I to P, because electrical, see, so we have seen about two types of valves. Okay, so in fact we have only seen about only one type of valve. So one is mostly control valve. Okay. Other one is, so control valve is mostly pneumatically operated. We have seen that. So pneumatically operated, which essentially means that it is. Am I audible? Is there any disturbance in my voice? Hello.
Your voice is breaking a bit. It's breaking. I cannot hear you properly.
Okay. Better?
Some kind, yes, sir.
Okay. So there are air to close and air to open. So two types of valves. We have seen it in a very detailed last time. So other types of valves are generally solenoid valves. Okay, solenoid valves essentially operate based on electric current. So you don't need a paranoid device. So that is what I'm trying to say. They are fully operated based on electrical signal. But so most of the problem with the solenoid valves are that they are mostly used for on-off. The precise control. So what is the advantage of control valve? So you have a control valve and you have a stem. Okay, and there is diaphragm and there is air. This is air, diaphragm, stem. This is plug. So, so control valve in generally, so you can, so the air acts, when air acts on the diaphragm, the stem either move up or down, and most likely precise control of the flow rate. But oftentimes the available electrical valves, which is also known as solenoid valves, which are there in the market, they are mostly on off. They will only use to shut off or open because they are energizing of solenoid.
So your voice is not clear.
Hello, is it hello?
Now it's better, sir. It gets distorted in between. I don't know how.
Oh, I'm sorry about that. Okay, so you please kind of flag me if my voice gets cut. Okay. So what I'm trying to say is, so if you look at an industry, you would predominantly see two types of valves. One is solenoid valves, and other one is control valves. Okay, so control valve is mainly used for precise control. That's what I told. So based on the airflow and the diaphragm control, you can precisely move this up and down. And the other sort of valve is solenoid valve. So solenoid valves are generally for on-off purpose. It is shut off. But it is operated based on electrical signal directly. So what happens in a valve? So solenoid valve will have a, it would mostly like this one. So it eventually you will have a plug here. And this would contain an electrical signal connection. And what happens is here there would be an electrical solenoid. So when there is electrical supply, sufficient supply, okay, the solenoid will get energized. So when solenoid get energized, what it would happen is it would just plug the flow. This may be your whole pipeline wherein you have fixed this, and this is your plug. When the solenoid get energized, so what it would just plug the flow fully. And when solenoid is de-energized, it would again go back. So there would not be any blockage. So the point here is that here you only need electrical signal. Okay, so now coming back to the ITP, what I am trying to say is if you are using a solenoid valve, you don't need an ITP. ITP again stands for high current speed pressure. So if you are directly using a solenoid valve,
My voice is breaking again.
give me a minute.
Sure.
Let me check. So I am now coming very close to the microphone. So if there is some problem, it is beyond that. It could be due to some network issue. So I hope this is much better, I guess. Still not? Hello.
Yes, sir. Good now.
Okay. Okay, so my argument that I was trying to say is if you this I to P element is needed only if you are fixing a control valve in a line. So if you are keeping a solenoid valve, you can directly keep the controller output AC, you can go to a cooling network. So now you have the control. Let's say you are controlling F2 as a flow, okay, to effect the air changes, the I to P would be communicating to the control valve, and also there would be an air supply. So both of them kind of interact together, and it would necessitate how much would be the opening of the line, and it would allow the desired control. So this was the overall. So every control system works like this. So now let's dissect and see how this. So see, we have just said that we only have a controller that helps you to do that. So the controller, there should be a brain. How controller works. So that's the problem. So let's say your original value is m. So let me call it as y measure. Okay, and other one is y set point. So y stands for the variable of input which you want to control, and you will have this error. So we are pretty much convinced that controller should reduce this error, because that is the metric, right? Because you have a set point which you need to know. For instance, let's say the purity of the outlet composition should be, let's say, 99. You measure it, and let's say you find it 0.98. Okay, so then you'll have to fix it something plus or minus to make it 99, because unless it is 99, 0.99 or 99% whatsoever, but your project would be rejected in the market. So this is your set point, and this is your measurement ym. So difference of that is your error, which is ym, which is that you are going to minimize. And a straightforward way, what we have seen here is, okay, the control action P would be some bias for some constant term times A times P. So I think, I don't know whether I have used the term E bar here.
It's breaking again. There's some problem with the network, I guess.
Okay, I'm sorry then. Let me just let me just try changing my microphone. 1 minute, whether that helps. Hello, hello. Could you hear me now?
Yes,
Yes,
sir.
sir.
Is it better or same, anything? So let's see, over the time you'll come to know, because I've changed my microphone, so this might be little helpful. Okay, so what I am trying to say is your control logic. So see, the controller output, which controller you need to take an action, right? So this the controller output is a constant times the some proportionality constant times error. Okay, so now the problem I'll tell you. So this is known as bias term, and this is known as proportional gain. Proportional gain. Okay, and this is E is for error. So technically speaking, it is P of t, because every now and then P would remain constant, okay, K would remain constant, E would be changing with respect to time, because your E is y set point minus y of t. Your actual value would change with respect to time. So this is a dynamic process. So your E would change, correspondingly your PT would change, then when the PT would change, what would happen? I to P, if I to P output would change, which essentially means that air supply will change, it would affect differential opening. So that's way overall this correction works, and this process would be continued until ET becomes 0. But the problem here is that ET can momentarily be 0, then it can again come in. So which essentially says that, so if you try to look at the profile of ET with respect to time, and ET is of course can be negative or positive. So what you might see is your error, which is this, which is the ET, and this is T. You most likely, the controller output would be most likely moving like this. So which means that there is some point it would be 0, which is fine. Otherwise, it is linearly increase or decrease with respect to the error. So the profile controller output would most likely follow a line like this. Sometimes it would be positive, sometimes it would be negative, so on and so forth. So now what is that it's going to bring in? So this controller output E of t would go to I to P. I to P would again communicate with your, what is the final thing? Final control element, which is what? See, final control element is another name. So this sometimes it can be valve. Most likely it would be valve, or if there is something. If, as I told, if there is another way to do this effect. So it is generally all the valves are called final control element because this is affecting the control. So this is what enforcing control action. So it is the final control element in the control loop. The whole thing, what you see here is a loop. You see, it starts from here, here, and this whole thing is a loop. So that's why it is fine. The last element in the loop. Okay, so now the problem what I am trying to say is so you have your control valve, which is pneumatically operated, and you have a plug and a diaphragm, and you have air and the diaphragm, and this is the signal from I to P. So sometimes what would happen is, so let's say your process output is like this, and this is, so let's say this is a target set point. Fine, and this is y of t with respect to time. I am showing the product output. It could be concentration. This is the set point, be it 0.99 or so. This is what your desired set point. It won't change with respect to time, and this is something that you need to achieve. So initially, you might start with somewhere here. Okay, then it might go. And you have seen the responses of second order systems and things like that, underdamped, overdamped. Sometimes it momentarily cuts your set point. Immediately your controller would be, what is your controller? P is equal to P bar times K E, both the sides. So when it just crosses this point, suddenly control action shuts off. Okay, then, but your dynamics is not ending here, right? So it might go up and down. Then what would happen? Again, your control action would start. So when you look at the valve here, so every time, so see, your controller is communicating to I to P, then I to P is communicating to your control valve. So every now and then your valve will get a shock whenever it crosses the set point. So essentially means that when it becomes 0, your suddenly the supply stops. The air supply stops. Then it changes. Then you would get then the valve would start opening. So if you try to plot the valve, so or if you start looking at the valve profiles, it would tend to oscillate because it would keep on changing with respect to time. When it shuts off, open. And also sometimes, let's say if the error is very large, what it would happen? It would suggest you to make a large P, right? So it is P of t is equal to P bar plus K times Et. Let's say E is very, very large. So P of t would become very large for sure, which essentially means that it would start supplying full power, full control power. And as a result, okay, this might go like this, too much, huge power. So the error is large and correspondingly this thing also high. And this essentially means that let's say it is open or closed, whatever be. Let's say it is an air to open valve, and your control, your stem would fully move up and there would be full flow. And again, if the error is large, it would try to open the valve further. But this being a mechanical device, it can only open. So see, this is the valve plug, and so this is how a valve is placed in a line. So let's say this is the line pipe. This is the valve plug. Okay. Then there is a stem, and eventually this is your valve, right? This is the way it works. I'm sorry. So you can supply full control action. The stem might fully move up. So you would see that. So you would see that there is full flow, which essentially means that it is full flow. But still, so error is not zero. So error will zero only when your y reaches y set point. So it has fully opened. So still your error might not be zero. So it is, let's say here, and still the error is there. The controller will suggest you to open up more. Open the valve more, open the valve more. But what it can do, so it has already opened its full bore, correct? So what it would happen is, so this would eventually result in saturation. You cannot do anything. So it has given its full power and finally opened the valve, but still your set point has not been reached. And this would continue. Sometimes, so that's what I told. If you have an error plot and you see if the error is very, very high, always the suggestion is to open the valve more, because it is K times Et, right? So eventually, if the error is high, your controller value is also high. So, and there is no point also. See, eventually, even if you try to push more and more, what it would try to do is it would try to push the stem up. But there is a diaphragm. Diaphragm would say, this is what I can do. But again, it would start supplying air more and more. And this would unnecessarily create a stress on the diaphragm. Because you are always trying to suggest open, but like it has done its job. Like you cannot do it anymore. So you have supplied your accelerator. Let's say you are driving the car and you need to you need to travel at, let's say, 120 or 140 kilometer per hour. You have pressed your accelerator at full blow. Okay, still the speed is not reaching. What you can do? You have done your duty. So in order to avoid this pressure on the valve, because eventually controller, you are not going to keep controller alone in the plant. You are always going to keep this integrated system that contains everything. So every component, including sensor, controller, I2P converter, or final control element, it is also known as actuator. Okay, so I would use three words: control valve, final control element, or actuator, because that is the mechanical component in the. So this is the only mechanical component that would act. So the sensor can be mechanical to some extent, but that's just sensors. So this would eventually result in unnecessary stress, wear and tear. So people would tend to clip the output of the P controller at certain thresholds. This is just to avoid unnecessary stress on the final control element, which essentially says that if the ET is greater than, let's say, some threshold, and ET is less than some threshold, because it's in terms of uh, uh, in terms of, it's not in terms of the magnitude with sign. If greater than certain threshold, less than threshold, you keep it that as the maximum value, so that your valve at least is safe. So now, so now what is that we need to see? Let me just check what all things. Did I miss anything? Okay, so we also talked about proportional band, which proportional band is another way to kind of specify a controller property. See, eventually this is a real field expertise. So you have to buy something and implement on real time. So when you are the engineer in the field, okay. So, and so see, these controllers could be assigned. So if you recall previously, either this controller could be hardwired, or soft. Software means that some computer would do this job. For smaller control loop, it would most likely hardwired. So how do you this is hardwiring? So we will see that. So you can use electronic circuits. Okay, because what it does? K times ET, right? So you can use some resistances, capacitance, most likely resistance, capacitance, or inductance. Any of these three could be used to make a circuit and effect this action. Otherwise, as I told, by means of software, you would take the signal to a centralized DCS wherein the programs are written and it gives you output. For isolated loops, so what do you mean by isolated loops? Which means that, see, it is all about economics. Okay, so you, when you start working in a plant, you will come to know. So so let's say this is a big plant. So I hope you guys got a chance to see big refineries or anything like of that sort. Some, have you went for any industrial visits or something? I hope you have done it at least once. Hello, hello.
No, sir.
Not even once.
No, sir.
My goodness. So anybody have seen a refinery physically? Spend some time. Can someone tell? Anyone? None? Shall I think in that way? Nobody has visited a single chemical plant till now? Hello? Hello?
No, sir, haven't been able to visit actually.
My goodness.
That's how COVID has impacted our visits. Maybe we could
Okay,
have
no,
a
no.
departmental
So
one.
I don't know whether, so my point is now just this. What I am trying to say, are you able to visualize what is happening in the field? So I'll try to give you an example. Okay. So if you, I don't know, at least when you try to see an image of the refinery, there would be many things. Okay. There would be heat exchangers, reactors, fluidized beds, crackers, uh, separators, huh? Many units. So starting from feed injection to production. You would be amazed to see. No, I would say it's strongly, I don't know. So, but I strongly recommend at least to go and watch a video in YouTube how a large chemical plant works. Why I am trying to say is the following. The notion of process control can only be understood when you see the scale of the plant. Okay, so when you do it in laboratory scale with, as I told, one reactor, there is nothing in there. The scale matters. So why I am trying to say is, if one person or few person deployed, you can do the control of such small systems. So this is not a big system. You have a reactor, some feed in control, that's all. But when you go and see a refinery or any of things, so it could be any production line. Okay, this need not be any chemical production. You can, it can be any manufacturing production line. So for instance, if you could get a, if somebody visits what you call Maruti Udyog and see how they are manufacturing what they call vehicles automatically, you would feel it, because it's such a huge line. And what you would really see is that, so these numbers, so maybe you would see heat exchangers worth 2500 heat exchangers in a plant. Everywhere heat exchangers. So you would see some 25 reactors or maybe 30 reactors wherever. So what you are really trying to do is, and this is whole thing is spread over maybe am I audible? Am I audible, guys?
Yes.
Okay, so now, and these are distributed. So this is a large field, okay? Count 1000 acres. Some part of this would be feed entry, and here it would be preparations. Here may be what you call heating, which means lot of array of heat exchangers. Here may be reactor. Here may be separators. Here may be what you call gas cleaning. And here it may be what you call, so you need to have, so so see, this is all production line, and also you need to have something known as utilities section, because you cannot run the plant like this, that requires steam. So that's steam section. So this, they are called utilities. Water, purified water, because many of them are very corrosive, right? So if the water contains, you cannot use water just like that. It has to be very special water that you use, so that otherwise line would get corroded. Steam, then water, what else? Air, because everywhere you need air. You see, see, your control valve require air. So something, let's say you in a plant there are 1000 control valves. 1000 is like minimum. You would see that 2000 to 3000 control valves, even more. So what is the air? So this is another unit, and this is all spread across this 2500, 2200 acres. And what is the size of this heat, what you call reactor? See, reactor may be some 20 meters high, 20 meters high, and maybe 20 to 30 meter wide, or 20 meter wide. So it's such a huge, wide in the sense diameter, such a huge thing. Sometimes it can be lean also, 10-meter dia. So you are seeing equipments for that size. Why? Because you are producing in large scale, right? Throughput is much large. So if you go and see the Jamnagar refinery, which is currently, I think, the largest one in India, and there are, you see, equipments worth size this, because unless they don't do mass production scaling, they are not profitable. So, so you have to do mass production. That's why the capacity of the systems are very huge, which essentially means that the and so which essentially means that if there is some minor problem, if there is a minor safety issue, the entire thing is in danger. Okay, so why I am trying to say is, so if 2000 acres something is spread and you want to control manually, and you might, and let's say you are trying to do fully manual, no automatic control. You will, so let's say if the pressure increases, you manually open the valve, this, that, everything, and you employed some 5000 people. Okay, still you will not be able to manage, because that many number of lines, you would see mad. And also see, you are now putting lot many human, like what you call elements into the loop. If one makes one mistake, it can have a domino effect, and eventually everything would be catastrophic. So in always, any production line, the first philosophy is that minimize manual operation. Owing to two things. One is manual error. Human beings are prone to making error. Manual error can happen. Okay. And the second is you are cluttering the area, cluttering the space. For instance, if there is a blast happens, and if there are 5,000 people there, everybody would be affected badly. But let's say there are only 100 people, huh, in that area. So you still will be able to save them. You may not be able to save all the 1,000 people, or maybe 2,000 people, or 5,000 people. But if it is 100 or 200, you would be preferentially saved. So the basic principle of automation is minimize manual operation. Okay. To achieve that, you would have, that's why we are going for control. And how do you do control? So control would be in one part of this whole thing, which I kept here, there would be a control station. So this would be fireproof, blast proof, everything, like, so that people can happily sit. No, there would be people in the field also for emergency work, but you don't go and measure a temperature in the reactor or something. This is all automated. And all these lines, you see, whatever signals that you made would come as a, there would be a very fast communication channel. So now people are even using what is known as, of course not in India though, abroad, sensors that can, we'll talk about that if you have time later. So see, so how do you measure? So if you need to measure, you insert a sensor. Sensor will have a wire because signal, right? And signal will go to the control station. So I'm just zooming in the control station what I have drawn here. So let's say this is control station. And nowadays, so there are smart sensors. Smart sense works Wi-Fi. So it senses here. There is no wire. Okay, so it would be just a Wi-Fi. So information directly coming in here. So what happens? You are minimizing cables. Why? What is the advantage? Why? What are you gaining out of it? Cables can be fire, can cause fire hazard, right? It can burn. But again, you will have to have a what you call redundancy. Sometimes, if the whole smart sensor work stops, then you are stuck. So you would, of course, you would do a balance. Okay, so now coming to this control station, which, as I told, which is fireproof, blast proof, and so on and so forth. Half of this parts would be servers, huge servers. Let me draw it in more centrally. And this is like a protective sheet, which kind of, and this all would be rack servers, not small ones, not like an HPC server, but with huge redundancy. So these servers, here where you would all the signals that is coming in, okay, and this would be stored in, and the server would have a, maybe part of it would be historian. Historian means that data storage, maybe in the what you call, in the level of petabytes. Okay, so eventually what I am trying to say is that is why when this big data revolution or industry 4.0 or whatever you kind of boast comes in, chemical engineers become the first beneficiaries. Because eventually it's all data, yeah. So you have a lot of data and people are sitting over here. So there would be big control panels in front of them, and they would see how the, maybe it is unit by unit. So there would be a control panel for reactors, there would be control panel for separators, and there would be dedicated engineers. They would be watching this. It's like a multi. So big display units and things would be varying with respect to time. And what you would do here, and that here is the backend. So here you have sensors, and some part of would be the controller in terms of soft. Basically, computational softwares, and it would communicate back. Okay. So now, when you run an industry, there is a trade-off. Sometimes, let's say this overall space, let's say contains, let's say 50K sensors. 50K is lesser, maybe 1 lakh more than that. If you want to put 50K sensors and drawing 50K sensors and its lines to the central unit, which is located here. Here is what it is located. Let's say one of your unit is here, and every time you need to bring in here and take a decision and send this decision back to this unit, which is farther away from here, unless it is critical, not necessary. Why? You are saving in terms of cabling charges. Again, so charges are fine, and also you are reducing the hazard, right? Fire hazard. So cable, any cable line, it's prone to. So let's say if there is a leak of steam in the line, okay, that can burn that can burn the entire electric signal line. Okay, as a result, you might not see these people who is sitting here, they like to real-time monitor, and they would give, and of course there is automatic control softwares, and you would do, for instance, these people who is sitting here, what they would do, they would change the set points maybe, okay, and tune the controllers if needed, so that whatever they wanted to achieve, so that your y actual is close to y set point, because they are the whole people running the show. If they were unable to do things well, because everything is centrally controlled, okay. Somebody makes a huge mistake, which they won't, because they have been extremely trained personnel. And so but there could be possibilities, like for instance, cable got burned off and you're getting incorrect readings here. They would only act accordingly, right? Many things missing. So some part of them has been controlled locally by means of hardware sensors, by means of, you can buy. So you can buy PID controllers. Let's say if you go to electrical market and ask for a PID controller, you'll be able to buy it. It's very cheap. How they are been doing it? So it's a circuit board which contains resistance, capacitance, and inductance, whatever way in which they would arrange it suitably to affect the logic of the PID controller or controller, whatever. It could be P controller, PA controller, or PID controller. Some of them would be controlled locally, and some of them require more attention, would be wired to the central control panel. And only people that is necessary in field would be roaming around. Rest all, so you won't see any clutter. So my point is, only if necessary, only you are going to draw lines and cabling. So some of them would be controlled locally. So that would request the hardware controller, hardwired. Some of them could be taken so that people can closely inspect. That you can do by means of soft controller, which means that control algorithms, people can change it, and the server wherein the whole thing has been coded would be operate accordingly and send the signal back. Okay, so I think from where we have seen and where we have went, okay, so what I am trying to say is hardware thing. So it's always good to do some part of the controller would be hardware, which depending upon the criticality, some variables have continued using hardware controller, some would be taken, and it's an algorithm, right? P is equal to P times K into ET. It is an algorithm. I'm saying all the algorithms are simple as this, but whatever possible is all control, and people can just do this entry from here and things would work. Now coming to how PI controller works. So you need to, so you eventually you are always looking at an overall performance. Okay, so P of T is equal to P bar times K into U of T. So eventually, how do you calculate the response of a linear system? So it is Y of S by X of S is a transfer function, and you will have to take the inverse, right? So we also need to bring in the effect of controller in the overall action. So first thing is to learn how to calculate the transfer function of the controller, because that is what we were doing. So P of t minus P is equal to K times Ct. Okay, and P of t minus P is like, let's say, P bar t by Et is K. So the which essentially means that the transfer function of a proportional controller is just a constant number. You see? So now coming to the, I think we have spent a lot of time in, but I think you should know this. So my sincere suggestion is maybe if you find this topic interesting, go to any YouTube video and watch how a control room or a control station works in an overall refinery. You would see like there would be a lot of variable coming in, somebody would be entering it, you would see the server. At least try to get a internalize what we are trying to do. It's very important. See, unless and what is our job? See, it's not a small job. The whole space worth what you call 50 acres, sorry, 2000 acres thing. You are controlling it from a control station like this. You see what is the plight here? So everything here is coming except something which is controlled locally. And why that is so? Because you cannot go and do everything at the what you call at the source level. So you take it back and do it in a safe position. This may be the safest position in the plant. Okay, so now coming back to the other type of controller. So what is the problem with P controller? As I told, one is it tend to see this would be happily oscillating. So this would keep on, if there is an error 0, E versus T, E versus E. So you would see that your control action would keep on oscillating like this. So what would eventually happen? Your output also keep on oscillating. Your Y of t would keep on oscillating. So can you tolerate that? For instance, some variables you can still tolerate oscillation. Can you tell me such variables? While some variable you can still tolerate some level of oscillation, not all, but some. By physically you can think. Can you think of? One is level. Why? Because let's say, I hope you might have seen how your tank fills in, right? When a tank is filling, it is already under, your meniscus is already under oscillation. So some level of oscillation, your control is also bringing some level of oscillation. So it may be always in tolerable levels. Because when you fill in, it actually brings in oscillation. So generally level controls, you can tolerate some oscillation. So your controller output is also varying. So when you use proportional control for level, it is okay. But many variable like composition temperature, you cannot kind of tolerate any level of oscillation. Flow is okay because inherently when you fill in the tank, it would tend to oscillate. So that level of, so if you can only reach certain accuracy even if you control the controller output. So see, if you could control it further, still when you start filling in a tank, it would tend to oscillate. So that would be always under what you call always kind of under what you call under acceptance level. So for instance, other variables like temperature. Temperature you cannot tolerate too much. Why? Because anything in the reactor the temperature play a key role. You recall Arrhenius equation, right? The rate law is very strongly depending upon the strong dependent on temperature. And also temperature can also, so let's say if a reactor temperature or reactor heats excessively and gets dried up, there is a very high likelihood that there is a blast or fire damage. So temperature is a variable that you generally don't like to have any more oscillation. Or many other, I'm telling one example, there are many, but level is still okay, because level, whatever you do, and when you start filling or discharging, the meniscus would keep on oscillating, whatever you do. So there is, so but even if you add some level of more uncertainty to it, it would be still in acceptance level. So to avoid such oscillations and also offset, so eventually what is the problem? Let's say your level that you need to control is, so this level is, let's say, 1 meter. Due to this oscillation, you may not be able to control at 1 meter. Sometimes you would only have 95 centimeter, some, or maybe 1.0, whatever. So there is some level of offset, and this is always tolerable with respect to the fact that your variable, when you fill in or emptying, would definitely oscillate. But if you want to get rid of that, there are other techniques. So you would bring in the notion of integral controller. Integral controller again is using the integral action. So here you would have a bias term as natural. There would be a scaling time, which is generally known as integral time, tau I. This is called integral time. So this integral time is a scaling factor like Kc there, but it's a divisor here, okay? And total error, it is integrated from 0 to t, and this is the factor. So there is, so technically there is one advantage of integral controller. One is it can eliminate offset. We will see how it, what does this means, okay? So let's say we try to plot errors with respect to time, and this is your set point, and here this may be error, and finally it controls. Assuming that it is controlled, this is the set point. Whatever is desired, and this is the way your y of t behaves with respect to t. So, okay, this is an error. So this is technically, if you calculate, let's say y minus y set point minus yt, this is what? Set point minus this. So this is a negative error, and this is going to be positive error. And again, you would see, because integral time, no, you have to compute everything. So integration, whole thing. So what you are going to do is, your error never, E of t, so this integral term never goes to 0. What the integral controller I, it is, okay. Again, P of t, if you use this notation, P bar, plus it is 1 by tau I times integral of E of t, pt. And it is of course 0 to t. What then if you want to put a dummy variable, you put star and things like that whatsoever. So what I am trying to say is, you would never see this error term going to 0, unlike sorry, the integral term is vanishing to 0 every time, because this would be positive, negative, positive, negative, positive, negative. So as a result, this integral action is always on. It's like a guard. It's fully guarded. You cannot keep the integral term off. Why? Because even if you sum everything, there would be some positive. So let's say it moves down, it is negative, then it moves back, it is positive. So there would be some residual error always. which essentially means that the integral action would be on always. That would eventually, so they will also call a very interesting term, asymptotically. See, this plus minus, this action, continuous action of the integral variable would asymptotically drive the error to 0, which essentially means that there won't be any offset. Okay, so it's 11. I will stop here. Okay, so do we need to have a doubt clearing session today, Ashutosh? What do you think? Or we will have it the next tutorial and push it to next Friday?
So I'll ask the class and let you know. In case if people want it, I'll let you know. If they don't, so we can put it up for next week.
Okay, because we have not started with the tutorials, right? So we will have the tutorials. Well, I am okay. I am available. It's up to you only.
Yeah. So if people want it, I'll tell you so we can have it. If they don't,
Perfect.
so
Perfect.
we can consider that it's not there today.
Okay, guys. Then I don't want to take up your time anymore, and see you guys next week, next Tuesday. I think. Bye bye.